your mic is on. So y'all have fun.
Thank you.
But we just get it fixed.
Went out in front and stopped you.
Yeah, and like just drove me, and I was trying to like swerve with it.
You got
You know the routine.
Yeah.
Their forms.
I'll like,
And I'll grab them afterwards.
I landed.
And there's only
Grab.
so have fun.
He was going maybe like 15 miles an hour, too. I was like, are you serious? You've been telling me, you've been bragging about fucking...
I sketched on the back of a car one time when I was a teenager, and I thought I broke my feet. I was like, they were going about 30. I was like, I'll never do that again.
How many people's in this class? How many people's in here?
11.
11?
Wow. Let me get that A. Too crazy.
Oh, you have to.
Because the guy still has a D in reinforced concrete. I couldn't take it. I'm still working for the highway department.
This is for recording the lecture. Could you please?
So our wastewater plants, or one of the wastewater plants, he's like, so I have dean meetings on Monday, so we can't have class on Mondays. Usually it's Fridays. And so he's like, it's gonna be Wednesday and Friday. 30 to 10. Cool. He emails us last night and says, well, if somebody has a class and I'll do it Friday, so I can't. I was like, if any class I can think of that's not static, you can't be in static. Oh, fuck.
I have a question. And it's not for this class. It's for concrete.
Yeah.
I don't have a ACI book, but I have a folder. The book's printed off on. Can I use that?
Yeah. It's the same version.
Yeah, but it's not a bound
I
book.
don't care.
Okay. Awesome. Thank you.
Oh, I got A's though.
No.
I got all these. It's your civil one.
Oh, okay.
Yeah, you have to go over 2.5 and civil.
Get that 2.5.
No, 2.5.
It's all C's. That's 2.5.
Well, I mean, I'll see, but if you have a D, it's 7.
Yeah. Okay.
Okay, so good morning, everyone. So today we're going to go through the syllabus, and we're just going to go through a quick revision on some things that we learned in Structure Analysis 1. Okay? So our lectures are Tuesday and Thursday, 9:30 to 10:45 in this room throughout the entire semester. My room is at 244 Life Science West. I guess all of you took classes with me before, so you know my room, and my email is listed here. The office hours is Monday, Tuesday, and Wednesday from 11 to 1. If you need an extra help outside those office hours listed here, you can just stop by my office anytime I'm there, or you can send me an email. Okay? The prerequisite for this course is CE 3213, which is Structure Analysis 1. So this course is a continuation of Structure Analysis 1. So what's the difference between this course and Structure Analysis 1? That's what we're going to discuss now. But for the textbook, since it's a continuation of Structure Analysis 1, it's the same textbook that we used in Structure Analysis 1. Structure Analysis by R.C. Hibler. Okay? So it's the same book. We covered, I guess, till chapter 7 or 8 in Structure Analysis 1. In Structure Analysis 2, we're going to cover around 4 more chapters. Okay? So what's the difference between this course and Structure Analysis 1? They are pretty much the same. We're going to do the same things that you learned in Structure Analysis 1 here in Structure Analysis 2. The only difference is we did it in Structure Analysis 1 for statically determined beams and statically determined structures. In Structure Analysis 2, we're going to do the same things, but for indeterminate structures. Okay? So what did we learn in Structure Analysis 1? You have a structure that can be beam, frame, or truss. That's what the type of structures that we dealt with in Structure Analysis 1. Okay? So we had those type of structures, beam, frame, truss. We, in Structure Analysis 1, we learned to find the internal forces in those structures. What is meant by the internal forces? There are 3 types of internal forces. Normal force, shear force, and bending moment. Okay? That was the main part of Structure Analysis 1. Definitely you learned more things in Structure Analysis 1, like the inference lines. You also learned things that finding the loading on structures using the ASE 7, calculating the deflection. Okay. Here we're going to also be able to calculate deflection at certain points in indeterminate structures as well. Okay, but using different methods. So you might think, okay, so that's going to be so easy. Not that easy, because in Structure Analysis 1 for determinate beams, all you needed to find the internal forces in determinate structures, all you needed was the equations of equilibrium. That's the only piece of information, the only knowledge we needed, okay, to find the internal forces in determinate structures. Just the equation of equilibrium. What was the equation of equilibrium? Sigma fx equals 0. Sigma fy equals 0. The summation of the moments about any point equals 0. Just those 3 equations, just using those 3 equations, you were able to solve your problem and find the internal forces, whatever that internal force is. Normal force, shear force, bending moment at any point. Okay? Problem with indeterminate structures is if you want to apply just those 3 equations, okay, it's not going to be enough. You need something more than just those 3 equations, okay? And that's what we're going to learn in Structure Analysis 2, how to solve this problem when the equations of equilibrium is not enough to find the unknowns, okay? The actions, for example, or the internal forces, okay? We're going to learn here. Mainly, we're going to learn 2 different methods, okay? One method is called the slope deflection method, okay? We're going to start with the slope deflection method. The slope deflection method is aimed toward beams and frames. It's not applicable to trusses, okay? You cannot use the slope deflection method to solve for the internal forces in trusses. You can only use it for beams and frames, okay? And then we're going to extend this method into another method called matrix structural analysis, okay? The matrix structural analysis is mainly like a simplification or an output of something called the finite element method, okay? The finite element method is what you used when you use the STAT software that you learned in structural analysis 1, okay? The STAT software is based on the finite element method, okay? So here we're going to learn how to use matrix structural analysis, which is based on the finite element method, okay? The finite element method or the matrix structural analysis that we're going to use can be used for any type of structure. So it can be used for beams and frames, exactly like the slope deflection method, but it can also be used for trusses, okay? So on the final, if you have a truss problem, the only method that you can use is the matrix structural analysis, okay? There is a lot of similarities between the slope deflection method and the matrix structural analysis. They are closely related. Mainly, the matrix structural analysis is based on the finite, on the slope deflection method that we're going to learn first. That's why we're going to start with the slope deflection method, okay? And then we're going to extend it, okay? It's not a different method, but it's like kind of extension to the slope deflection method. You just put it in a matrix form because computers can work with matrices much easier, okay? So that's pretty much what we're going to do, okay? In terms of learning, something new that is in the textbook. The other important part of our course, okay, is the steel bridge competition, okay? So in our course, okay, we're going to prepare you, okay, to start working on the steel bridge competition. So the ASCE along with the AISC, okay, they perform a competition during the spring, okay, between the universities, students in the universities. So this is related to the ASE student chapter, okay? This is an activity for the ASE student chapter. So you have to build a bridge, okay, with certain requirements, okay, and the best bridge in terms of deflection, okay, in terms of weight, in terms of, how beautiful is the bridge, okay, wins the competition, okay? So part of our course is each one of you is going to work on a design for this bridge, okay? And then we're going to merge you into maybe 3 groups, okay? So you're going to work together, each group, you're going to see what designs you have, okay, for each member in the group, and you're going to start finding the best one, and then you're going to start optimizing this design, okay, to try to win the competition, to try to make this bridge the best in terms of the criteria for winning the competition, okay? So that's going to be an important part of our course as well, okay? So how you're going to do this? You're going to use the STAT software that you learned in Structural Analysis 1. You're going to model your bridge, okay, using the STAT software as you learned in Structural Analysis 1, and then make changes to that bridge to make it better and better and better. It's an optimization problem, okay? And in a try to, make the best, bridge design, and then whoever is interested in moving forward with, the ASE student chapter during the spring semester, working toward, building that design. So the design that you're gonna, this class is gonna come out with, okay, is the design that is gonna be, used to represent ASU in the steel bridge competition. So it's an important task, okay? It's not just for the class, okay, activity, and that's it. No, the best design, okay, is going to move forward to actually represent ASU, okay? So we're going to move toward that. So the thing is, you're going to start as individuals, okay? So each one is going to start, reading the rules for the competition, summarizing them, understanding them, writing an initial report of what he got from the you know, the requirements for that bridge, okay, and then each student is gonna, you know, give a design, okay. You might say, I don't have any idea. Any simple idea, okay? Any idea is gonna work, okay? You just want to see how you would think of a bridge design, okay? That would fit the requirements. The most important thing, the ASE gives some rules that you have to follow. Just get out, you know, just get any design that follow those rules, okay? It doesn't have to be the best design, okay? That's what we want to do during the semester, to start with different designs and then get the best design. So don't worry about, oh, this would not be the best design. No problem. As long as your design is adhering to the rules, you're fine, okay? That's what I want from you, to get a design that is adhering to the rules. But if you get a design that is not adhering to the rules, you're going to lose points, okay? Because you don't understand the rules. There is limitations to the bridge that is given by the rules, okay? How high is the bridge, like the size of each element? There are some rules. So you're going to start first reading the rules so that the design that you're going to, you know, propose adhere to those rules, okay? You should not start, you know, just giving a design. You first have to read the rules, and that's going to be the first test for you all, okay? To read the rule and write the constraints that is given in those rules, okay? And the criteria for winning the competition. So there are two different things. The constraints that, you know, those are the limits. You cannot have a member longer than a certain length. You cannot have a, you know, the bridge with a certain height, okay? So those are the constraints. And then there are the criteria for winning, you know, the competition. So although your bridge is within those constraints, but there is the criteria for winning, like the main three criteria, for example, is the weight. Okay, this is usually, you know, every year, like this year, the rules are not published yet. Once they get published, we're going to start working on this. But usually the criteria are like the weight. You need to minimize the weight of the bridge. The deflection, you need to minimize the deflection at certain points, okay? And the time, of the construction time, okay? You need to build this or get a design that can be built within a minimum time, okay? So you need to understand those things, okay? So that you can, you know, later on try to minimize those values, okay? Definitely, as you see here, okay? There are like the weight and the deflection. To minimize the deflection, you need larger sections, right? Having larger section means that the weight is going to be high. So that's, you know, an optimization problem, okay? You have to come to the point, you know, and try different designs where, you know, this is the least weight along with the least deflection that you can get, a combination of both of them, okay? So that's what you're going to be working on with the steel bridge competition, okay? The steel bridge competition, as you see here on the on page 3 in the syllabus, okay? The grading for the project, the steel bridge competition project, it's 25% of the grade for this course, okay? So that includes all the reports and presentation. You're going to be giving 2 presentations through the semester, okay, for your designs. So as I told you, you're going to start as an individual, okay? You're going to get a design for that bridge, and then later on we're going to merge you into 3 groups, okay? So each group will have maybe 3 or 4 students. You're going to have 3-4 different designs. You're going to try to mix them to have the best design in your group, okay? And try to optimize this, change the weight of a member, okay? Change the dimension of some members, try to, you know, see how to get the best result out of that. I'm going to be, you know, giving you advices, and so don't worry about that, okay? But just right now, I'm just letting you know, how this part is going to be, okay? Any question? Okay, so definitely you're going to be using the stat software. So If you have some time, you can refresh your information about the STAT software, okay? Going through the syllabus here, those are you have the course learning outcomes, the things that we're going to cover, okay? We're going to calculate the internal forces in statically indeterminate beams and frames using the slope reflection method, and calculate the internal forces in statically indeterminate structures that include beams, frames, and trusses using finite element modeling, and then the design and build a steel bridge to compete in the ASUCE steel bridge competition, okay? If we have time, we're going to cover part 4 here, which is using ASE7 as we did in structure analysis 1. So in structure analysis 1, we used the ASE7 to find loads, the dead load, the life load, and the wind load. Everyone remember this? Okay? So if we have time, we're going to use the ASE7, but here to calculate the only load, or one of the loads that we didn't cover in structure analysis 1, which is seismic loads, okay? Earthquake loading, okay? So that depends on whether we're going to have time or not. So the contribution of our course toward the program outcomes, toward the civil engineering degree, okay, it serves for outcome 1, 4, 6, 10, and 11, okay? So our course, so outcome one for our program, those are the ABIT requirements, okay? So the ABIT, okay, to give accreditation to our program, so that your degree, your civil engineering degree is accredited by ABIT, okay, it has to fulfill certain, your degree has to fulfill certain requirements, okay? It's, there are 11 requirements. Our course fulfill 5 of those requirements. How does our course fulfill those requirements? Let's see here, outcome 1. Outcome 1 is our program, okay, not our course, our program, our civil engineering program has to give students a good understanding of mathematics, science, and engineering, and ability to apply this knowledge in engineering practice. Definitely that's what we're going to be doing in our course, okay? We're going to use math, we're going to use a lot of math. I only teach, all the courses I teach are all math-based, okay? It's all equations, matrices, solving equations together, formulating equations, okay, to solve our problem. And it's based on science. It's all based on Newton's first, second, and third law, okay? It's all based on equilibrium, okay? So it's based on science, okay, and it serves to solve engineering problems, okay? So at the end, we use math and science, okay, to solve and find deflection and find internal forces in a structure, right, which is an engineering problem, okay? And then outcome 4, it's an ability to identify, formulate, and solve engineering problems. Definitely, this is the main task of our course, okay? We're going to identify what type of structure you have, the loads you have, okay, and understand and formulate this problem into equations, okay, and then solve it to find something, definitely, you know, engineering problem, which is finding the internal forces, okay? So, this is outcome 4, okay? And then for outcome 6, it's an ability to communicate effectively both orally and in writing, okay? Definitely our course contribute to this outcome because you're going to be giving written reports and oral presentations for your steel bridge competition, okay? Designs. So that's how our course contribute to outcome number 6, okay? You have to have, or this course will give you the ability to communicate effectively both orally and in writing, okay? Outcome 10, all graduates will have an ability to use the techniques, skills, and modern tools necessary for entry-level practices in the area of concentration. So definitely in our course, you're going to learn, or not learn, you're going to use STAD, right? The STAD software for your steel bridge design, okay? Which is, you know, the modern tool, one of the modern tools used in the engineering practice, using softwares to find the internal forces, okay, in indeterminate structures. And then outcome 11 gives you the ability to analyze and design a system, component, or a process. So you're going to be designing your steel bridge, okay, to meet the requirements given by the ASUCE competition. Okay, so to meet those requirements, you're going to give a design that meet those requirements, which is typically outcome number 11. Okay, so this is how our course serves the ABIT requirements for the program outcomes. Okay. Accessibility resources. If any one of you has any disability that need accommodation, please contact the disability services. They are located at 2181 in the student union, and the telephone number is listed here in your syllabus. If you're gonna do so, please let me know as soon as possible. Okay. Then the rest here, I guess you know all of this. Copying from your colleague is not permitted. You can, collaborate together, but you cannot copy from your colleague. Okay. No cell phones are allowed during the exams, typically, and during the classroom. I don't want to, you're not supposed to use your cell phone during the classroom. Talk to your friends. Okay. The most important thing during the exams: no cell phones, no electronics, no smartwatches whatsoever. Okay, that's very, very important thing that I really care about during the exams. No electronics, especially smartwatches. Okay. For this course, we're gonna have 3 exams. 2 midterm exams and 1 final. Each one is 20% of the grade, so that's 60% of the grade. 25% of the grade goes to the steel bridge competition project, okay? And 15% is for homeworks, quizzes, attendance, class contribution, everything else is 15%, okay? How I will distribute those 15% depend on the class average, how you behave, I might have just 5 points for homework and 10 for attendance, or 5 homeworks, 5 quizzes, 5 attendance. So it's not something set. It's all 15, but it depends on how the class performs. Okay? Any question? And then here on the last page you have the points, how much points you need to get an A, B, C, or D, or F. Okay? If you need to get an F, just don't come to the class. Okay. But the points that you have here, okay, it's not strict. Okay. Usually the class average might move those, a little bit down. Okay. So that depending on the class average, I can move this for the favor of the student. And then the lecture and the exam schedule is listed here. We're going to cover chapter 11, that's the slope deflection method, and we're going to cover chapter 14 and 15, okay? Chapter 14, 15, and 16, okay? This is matrix structure analysis in the textbook, okay? And there is some lectures or some part of the course that is, devoted toward the steel bridge competition. This is not going to be I have, week 4 to 7 for that, but they're going to be scattered throughout the entire semester, okay? It's not going to be like 2-3 weeks back to back. No, we can spend some time maybe next week, once the rules get published, okay? We're going to spend maybe half a lecture or maybe 1 lecture discussing the rules together, okay? So, for the midterm exams, the first midterm exam is going to be October 4th. The second midterm exam is November 15th, okay? Again, those are not strict. Those are the allocated times, but as we approach the midterm exam dates, okay, if everyone in the class needs to change this, we can change it as long as everyone in the class agrees on that change, okay? Any question? Okay. Great. So let me see the attendance here. Who's missing? So everyone is attending. Okay. So those are the 11 students just for the class right now, okay? So I just need you to be familiar with your colleagues, okay? Because you're going to work together in the steel bridge competition. You're 11 students, so if we break you out to 3 groups, so each group is going to be 2 groups are going to be 4 students, and 1 group is going to be 3 students, okay? So if you have any preference of who wants to work with who, just let me know, okay? Otherwise, I'm going to divide you myself, okay? Any question? Okay, great. So today we're not going to get any or do anything new, okay? It's the first lecture, so I don't want, to put a lot of, work on you on the first lecture. So today I'm just going to solve a couple of problems, okay, from Structure Analysis 1, just as a revision of what you learned in Structure Analysis 1, because this course is very, related to Structure Analysis 1. If you don't know how to write a bending moment diagram, a shear force diagram, calculate deflections, all those things, okay, you're not going to be able to succeed in this course, okay? That's why this course, okay, has a prerequisite, which is Structure Analysis 1, okay? So right now, I'm just going to, give a simple revision, okay, on drawing the bending moment diagram in determinate beams. So example here on beams. So in this example, we're going to have this compound beam So this is point A here, point B, E, C, D. The distance is here. This is 6 meters, 2 meters, 6 meters, and then 10 meters. Okay? The loads applied on this beam, so here, again, just a revision, a reminder, those are supports. You need to know the type of supports, roller support here, hinged support. This is not a support, this is just the connection between the 2 members, okay? Member AE and member ED, it's a pinned connection, okay, between the 2 members. It's not an external support, okay? There is no external force applied on the structure here due to the support, okay? It's just 2 members connected together at point E, okay? It's a hinge, okay? Internal hinge. At point A here, there is an upward force of 40 kilonewtons. From A to B, there is a uniformly distributed load of 20 kilonewtons per meter. And then from B to C, there is a uniformly distributed load, but with a less intensity. It's 10 kilonewtons per meter. And then from C to D, there is another uniformly distributed load with a higher intensity of 20 kilonewtons per meter. In this example, you're required just to draw the bending moment diagram. Okay? So, solving this problem, since today is a revision, so let's refresh, our knowledge how to solve this type of problems. How to draw the bending moment diagram. To draw the bending moment diagram, the key thing is, okay, you need to calculate the moment at the key points. key or critical points. What are the key or critical points? Does anyone remember this? Yes, A and D, but why A and D? What are the critical points? Like, not for this problem. Generally, what are the critical or the key points?
The start and the end.
Okay.
Supports.
Okay. What else? So you said the start and the end. Okay, so let's write this. The start and the end of each member. Okay? What else? So here, if you consider this beam as just one member, so it's going to be A and B. What else? You said the supports. Yes, so you have to find find the moment at the supports, but I'm not going to write the supports. There's a more general definition for the support point. Okay, what would that be? You have to calculate the moment at any point where there is a concentrated force applied. When you have a support, the support gives you what is the effect of the support? There is a force due to this support on your structure, right? So whether this force is due to the support or just an external force like this one, this is a critical point. This is a key point that you have to calculate the moment at. Okay? So the second point here is points with concentrated forces. Okay? What's the third key point? What about the uniform loads? For any uniform load, okay, you have to find the moment, okay, or calculate the moment at the beginning and the end of each and every uniformly or, of any distributed load, whether it's uniformly distributed or linearly distributed, okay? So the beginning and the end, or the start and the end of each distributed load. If you miss any one of those three, you're going to draw the wrong bending moment diagram. Your bending moment diagram is not going to be correct. Okay? You have to find the moment at each and every point of those key points. Okay? And then you connect them, okay? Either by straight lines or by a curve, a parabola, okay? When would you connect them by straight line and when would you connect them by a parabola? If the two consecutive points, there are no loads between those 2 points, then you connect them by straight line. If there is a uniformly distributed force or a linearly triangular force, then you have to connect them. There is a parabola. Okay? There is a curve. Okay? So let's write this. The bending moment diagram changes linearly. What does linearly mean? It's going to be a straight line. Between key points if there are no distributed forces between them. And if there is distributed forces, then it's not a straight line. It's a parabola or a curve. Okay? So here we said to draw the bending moment diagram, you need to calculate the moment at the key points. Right? And we listed the 3 key points that we need to cover. Okay? So let's see here. What are the key points in this problem then? What are the key points? The start and the end of the beam. What are those? Point A and point D. So you have to find the moment at point A and point D. And then the start, the points with concentrated forces. Where are the points with concentrated forces? Point A, there is a concentrated force of 40 kilonewtons. Point B, there is a concentrated force here, because when you go or try to draw the free body diagram, the support here, this support, it's a roller support, it will give you one vertical reaction, right? And also here at point C, it's a roller support as well, so there is a reaction, a vertical reaction, that's a concentrated force as well. And point D, it's listed twice, so you're going to have to calculate the moment at point D because it's the end of the beam and because it has a concentrated force. Okay, so you need to calculate now the moment at point A, B, C, D. Okay, and then the third key point is the start and the end of each distributed load. So here we have a distributed load from A to B, right? So you have to calculate the moment at A and B. We already are going to calculate the moment at A and B because they are, they have concentrated forces. The point E is the start of the beam. And then you have another distributed load from B to C, right? So you need to calculate the moment at B and C. And then from C to D, so you need to calculate the moment from C to D. What about point E? Point E is an internal hinge, right? There is no concentrated force at that point. So you don't need to calculate the moment at point E. Okay? You only need to calculate the moment at point E in just one case. What would that be?
40.
No. You need to calculate the moment at point E, okay? If you're going to break your beam into 2 different beams. If you consider the beam as just one beam, then you're good, okay? But the thing is, when you calculate the moment at point E, this is a division, okay? Remind me. Point E is an internal hinge. How much is the moment at point E?
0.
0. It's always 0. Don't worry about, asking this question. How much is the moment at point E? It has to be 0. It's a hinge. Okay, it's an internal hinge. What is an internal hinge? An internal hinge is a point where it cannot resist moment. So definitely there is no moment at this point. If there is a moment at that point, it means that your structure is not stable. This moment will cause the member to rotate. There cannot be any moment there. Okay? So now we need to calculate what we realize that the key points are point A, B, C, D. Okay, 4 points. So I have to calculate the moment at those 4 points. How to calculate the moment? Okay, that's the question or the thing that we want to remind ourselves of from structure 1. Okay. How to calculate the moment at the key points. So the moment is one of the 3 internal forces. So just let's have a reminder about what are the internal forces. So when you have a member like this, okay, and you come at one point here, okay, you break your member, okay, to 2 parts. Those 2 parts, okay, are interacting. We're interacting together. The interaction is the internal forces. Okay, so the internal forces, you have 3 types of internal forces. A normal force that is in the direction of the member, and that's the positive direction of it. Shear force like this, V, this is the positive direction, this is the shear force, and then this is the bending moment, M. Okay? So to calculate any of those three internal forces, you need to break your structure at that point where you are interested in finding the internal forces. Okay? So here, let me write this. So to calculate the moment at any point, take a section at that point that you want to calculate the internal force at, breaking the beam into two parts and simply apply the equations of equilibrium to any of the two parts. So let's do this now to find the moment at those key points here. Okay? So the key points are point A, B, C, and D. So now for point A, how to find the moment at point A, the internal forces at point A. What did we say? How to calculate the moment? Break the beam, take a section at that point. We'll break your beam into two parts, right? So at point A, I need to take a section. I need to break my beam here at point A into two parts. What are those two parts? Everything here and nothing here. And then we said study any of those two parts, right? Use the equilibrium of any of those two parts, right? It's up to you what part you want to study, the left or the right part of that section. Which one would you prefer? The left. Why the left? Because there is nothing on the left. So that means that MA is 0. Okay? It's that simple. So MA is 0. Okay? And then we want to find the moment at point B. The other critical point or key point is point B. So I would like to find the moment at point B. How can I do this? I have to take a section, point B. It will break my beam into two parts. Part on the right of point B, part on the left of point B. And then apply the equations of equilibrium to find the internal forces. Okay? The moment, maybe. So when I take you have to take the section at the point, okay? At point B. So which part would you like to study? The right part or the left part? The left. Definitely the left. Why definitely the left? There is less forces on the left, and there are no unknown forces on the left, while on the right there are unknown forces. What are those unknown forces? The reactions Cy and the reaction dy. You don't know how much are those. We didn't calculate them yet. Okay? So if I'm just interested in calculating MB quickly, okay, just studying the left part. So let's take a section at point B and see how to calculate MB. So that's point B here. That's the free body diagram of the left part of the section. That's point A here. And let's draw all the forces here. So we have here 40 kilonewtons, and we have this uniformly distributed load of 20 kilonewtons per meter. what's the length or the distance from A to B? What's the length of that part, AB? It was 6 meters. Now I took a section at point B, right? So taking a section at point B, I'm going to see those internal forces, the shear force, PB, the normal force, NB, and the moment, MB. Okay? For this uniformly distributed load, I cannot deal with this uniformly distributed load right now. I need to find an equivalent force to it. Okay? How much is the equivalent force and where would it be applied to be equivalent to this uniform load? I want to remove this uniform load. Okay? So it's the intensity of the load, 20 kilonewtons per meter, multiplied by the length over which it's applied, which is 6 meters. So this is 120 kilonewtons. I'm just going to put it in a circle, okay, to remind myself that this is not actually a concentrated force. It's just an equivalent force to the distributed load. Okay? And where would you put it so that it would be equivalent to that distributed load?
3 meters.
Right in the center of that load. So if the length here is 6, so that distance is 3 meters. Okay? Now, we would like to apply the equations of equilibrium to find MB. We just want to find MB. We don't want to find, I didn't ask you what are the internal forces at point B. We just want to find MB, just the moment. Okay? So how would we find MB? So take the summation of the moments about point B. The summation of the moments about point B is equal to 0. What do we have? We have 40 kilonewtons times 6 meters, right? It's rotating in a counterclockwise fashion about point B, so it's rotating in a clockwise, so that you can say that this is negative. So I'm assuming here clockwise is positive, okay? And then you have positive 120 kilonewton multiplied by its distance, which is 3 meters. And then you have MB, okay, which is positive as well. So from this, I can find MB. So MB is going to be negative 120 kilonewton meter. That's the moment at point B. Definitely, you're, junior or senior student now. You don't have to do this every time. You can just imagine this section in your mind, okay? You don't have to go it on the paper. This is not what I expect from you, at this moment, okay? This is just, since it's a division, so I'm drawing this. But later on, you can just say MB is 40 times 6, okay? It's a negative moment, and 20 times 3, it's a positive moment. That's it. Right? It just comes from the equation of equilibrium. But you don't have to draw the section each time. Okay, you don't have to draw the free body diagram and the section and show the three internal forces. I'm just doing this to, remind you of how things work. Okay? But you don't have to do this, and you should not do this. Okay? To save yourself time, So this is MB. So now we would like to find, the rest of the the moments, the moment at the key points. So now we found MA, we found MB. We still need to find MC and MD, right? What about MD? Yeah, you take a section at point D. So you have nothing here and everything here. So which part would you prefer to study? Definitely the right part of the section, so MD is 0. So usually for n points, point A, like point A and point B, the moments are 0, unless there is a concentrated moment. either it's, you know, an external force applied on the beam, external moment applied on the beam, or it comes from a fixed support, okay? Otherwise, the moment at the endpoints, they're going to be zeros, okay? So, but if it's a fixed support, definitely there will be a moment due to the reaction, there is a moment reaction at the fixed support, okay? So MB is 0 as well. Sorry, MD is 0 as well. So here we have MD, it's equal to 0. The only point left now is point C. How much is the moment at point C? So how to find the moment at point C? You take a section at point C and either study the right part of the section or the left part of the section. Right? Which one would you prefer? The right side. Okay, so the right side. If I study the right side, how much would the moment be? All the forces multiplied by the distances. What are the forces here? This is a uniform load, so you can just remove it by an equivalent force, which is how much? 20 times 10, so it's 200 multiplied by 5. What else? Is that it?
Your MC.
There is a vertical force here. If you draw the free body diagram, okay, there is a vertical force here called dy due to this reaction, right? There's a reaction force here. So you have to multiply dy by 10, right? How much is dy? You have to calculate it. You not assume it's 0. Why would it be 0? You have to calculate it. How can you calculate the reaction? Using the equations of equilibrium. Okay? So the free body diagram, then use the equations of equilibrium to find the reactions. Is there a way that we don't calculate the reactions? Let's see. If you use the left part of the section, would you be able to do it? Just find the internal forces without calculating the reactions? No, if you use this part, you're still going to need to find how much is By. Okay, so you either, choose the left part of the section or the right part of the section. You're going to need either By or Dy to be calculated to be able to calculate the moment at point C. Okay, so unlike point B, if you use this part, you would not need any of the reactions. If you use this part, you needed to know some of the reactions. Point C, you need to know or start calculating some reactions. So let's see here, how would we calculate the reactions? So this is a compound beam, okay? So for a compound beam, to calculate the reactions, you can draw the free body diagram of each part of the beam if you want. So what are the parts of the beam? This is one part and this is another part. So let's draw the free body diagram of each part of those beam, each part of those beam. So calculating the reactions. So someone would, if you remember, from structure analysis 1, we usually have calculating the reactions as the first step in the problem, right? Do you remember this? We calculate the reactions first. But here, we're not actually interested in calculating the reactions. This is not what we're looking for. We want to calculate the bending moment diagram. So if you can draw the bending moment diagram, okay, without calculating the reactions, don't calculate the reactions, okay? You're not required to calculate the reactions. If you don't need them, don't calculate them, okay? Don't waste your time and then come at the end, oh, the exam was long. No, the exam was not long. You just calculated the reactions that you didn't really need, okay? You just wasted your time calculating things that were not required, okay? But here, actually, no. I need to calculate the reactions to reach my goal, which is, finding the internal forces. So we're going to draw the free body diagram of each part here. Draw the free body diagram. So we had part A, E, and then part E, D. On part AB, at point A, there is a 40 kilonewtons going up. And then here we had point B. At point B, so let's see the problem. At point B, okay, there is a vertical action, By, okay? Is it go upwards or downwards? Is it upwards or downwards? This is the action. Is it upwards like this or downwards? I don't know. I'm your professor and I don't know. So, okay, you don't know before solving. It might be upward, it might be downwards, okay? So you have to assume something, okay? But this is not, it might be wrong, correct, or it might be wrong, okay? So don't, just stop. I don't know whether it's going to be up or down. I'm not going to solve the problem. No, just assume one direction and continue solving, okay? From point A to point B here, over this 6 meters of length, there were a uniform load that is equivalent to 120 kilonewtons right in the middle. Just going to put it in a circle, okay? And then from point B to point E, this is 2 meters long. There were a uniform load with a 10 kilonewtons per meter intensity. So this is equivalent to 20 kilonewtons. Okay? So this is the free body diagram of part AE. You agree with that this is the free body diagram of part AE? Are we missing anything? Or that's it? I don't like to call them reactions, okay? Let's call them the interaction between the two parts, okay? Because they are not reactions, okay? There is no support to the structure at that point. It's just two parts, that are connected together, okay? So here there are two forces, EY and EX. How did I know that EY is going up? I just assumed that. It might be wrong, okay? I don't know, but I have to assume something here, okay? And then let's study, so this is the free body diagram of this left part. Now we want to draw the free body diagram of the right part, ED, okay? So at point D, there was a support, okay? So we have DY. And then we have point C here. At point C, there was a support, so there is a vertical support CY, okay? From E to C, from point E to point C, it's 6 meters long, and there is a uniform load of 10 kilonewtons. So this is 6 meters, and there is a uniform load, so I'm just putting the equivalent force to this uniform load. So it's 10 times 6, so it's 60 kilonewtons. It's right in the middle between point E and point C. And then from point C to point D, that's 10 meters long, there were a uniform load of 20 kilonewtons per meter. So the equivalent force here is 20 times 10, so this is 200 kilonewtons. Okay? Anything left? Anything missing?
EX, EY.
EX and EY. Okay? They are exactly the same magnitude as those ones. Okay? What about their directions? The opposite. Okay? So if EX on the left part was going to the left, now it's going to the right here. If EY was going up, so EY here is going down. All of this might be wrong, okay? EY might be going downward, and this one might be going up, but I have to assume something, okay? So that I can start solving the problem. So now, let's go ahead, okay? At point B here, this is called BY, okay? So let's go ahead and try to find those, reactions. So which part would be easier? The left part or the right part? What are you interested in actually finding? Why are we doing all of this? Always remember, okay? Why are you doing anything, okay? Why are you doing this? To find dy or by. You just need one of them, right? To find the moment at point C. Right? Okay. So if you want to find dy, would it be easy to study this part to find dy? How many unknowns do you have here? 1, 2, 3, 4. How many equations of equilibrium do you have? 3. It's not going to work. Okay? You won't be able to find dy in a straightforward manner. Okay? You need to study this part first. Okay? So to study this part, since you can study this part anyway, to find dy, why would you find dy? Just study this part and find by. And that's it. And use by to find the moment at point C. Okay? So now, how would you find by?
Fine.
You have the equations of equilibrium, 3 equations of equilibrium. Sigma fx equals 0, sigma fy equals 0, sigma moment about any point equals 0. Would sigma fx be useful to find by? No, sigma fx is useful to find ex. I don't care about ex, it's 0 anyway. Okay? Sigma fy equals 0. What does sigma fy mean? Sigma is the summation, f is the forces, the summation of the forces in the y direction, equal to 0. What are the forces in the y direction? You have this 40, 120, 20, by, ey. So if you write this equation, you're going to have 2 unknowns, by and ey, right? So I don't want to use it. I just want to go to the point, okay? Which leaves us with the third equation, the summation of the moments about any point equal to 0. So where would you take the moments to find by?
E. E.
E. Why E? Why not A?
Because then you're left with E
Because
as
if you
a...
take moment about point A, by is going to have moment about point A, and ey is going to have moment about point A, and ey is not known as well, right? So it's going to be an equation 2 unknowns. So I want to eliminate ey, so I have to take moment about point E. So let's take the summation of the moments about point E. So let's say counterclockwise is positive. So you have 40 kilonewtons times, what's the distance? 8. Is it clockwise or counterclockwise? Clockwise, so that's negative. And then you have the 120 kilonewtons, this 120 here, multiplied by its distance. How much is this distance from the 120 to point E? 5. 2 plus 3, so it's 5 meters. So times 5 meters. Is it positive or negative? What direction are we taking about? We're taking it counterclockwise, so it's positive. By multiplied by its distance. What's the distance between By and point E? 2. Is it rotating clockwise or counterclockwise? Clockwise, so that's negative. What else? The 20. Okay? You have 20 kilonewtons. This 20 kilonewtons over here, multiplied by its distance. How much is this distance? 1 meter. So multiplied by 1 meter. Is it positive or negative? It's counterclockwise, so that's positive. Anything else? That's it. So this is equal to 0. So from this equation, you're going to be able to find By. By is going to be equal to 150 kilonewton. Positive 150 kilonewton. What does positive mean? Upward, downward? Doesn't mean upward or downward. It means that your assumption is correct. Okay? Your assumption for By was correct. So I assumed it's upward, so that's correct. Okay? If you assumed that it was downwards, you would just get the same value, 150, but you would get negative 150. It means that your assumption was wrong. Okay? It's not downward, it's upward. Okay? So now we have By, we calculated By, it's 150. Now we want to find the moment at point C. How to find the moment at point C? Take a section again at point C, here, and either use the left, study the left part or the right part. Which part would you use now? The left, because you know how much is By. If you use the right part, you need to find By, which is going to take more steps, right? So I'm just going to use this part because I have everything here now, okay? So let's draw the free body diagram here quickly, okay? So this is point C, so you have VC, MC, NC. What do you have here? You have point A here. You had 40 kilonewtons going upward at point A. You have point B here. You have By, which is 150 kilonewtons, right? And you have, in between point A and B, you have a force, a distributed force that is equivalent to a concentrated force of 120 kilonewtons, right? And then here, from B to C, this length is 8, you have 10 times 8, it's 80, okay? It's right in the middle, so this is 4 meters, this is 4 meters, and this length was how much? 6 meters. What about EY? Where's EY? I didn't break the beam. Point E. EY is the interaction between the two parts. To see this interaction, they have to be 2 parts away, right? If they are merged together, you don't see this interaction, right? So there is the force at EY doesn't appear here, okay? It only appears if you break the beam at point E, okay? So now, how much is MC then? So MC, this is how I'm going to do it now, okay? You just use it from the equation of equilibrium. So this one is going, it gives you a positive moment. This one gives you negative moment, okay? If it's bending up, okay, it's positive moment. If it's bending down, so it's a negative moment, okay? So 40 is positive. How much is that then? It's 40 kilonewtons multiplied by this distance. How much is this distance? 14 meters. And then negative 120 kilonewtons multiplied by this distance. How much is this distance? 4 plus 4 plus 3. So 11 meters. And then By. By is bending up, so this is positive moment. 150 kilonewtons multiplied by its distance, which is 8 meters. And then 80, negative 80 kilonewtons multiplied by 4 meters. Anything else? That's it. That's MC. So MC is positive 120 kilonewtons meter. Okay? So now, what did we do? We just found the moment at the key points. Okay? the 4 key points. What is left now? Just plot those moments, okay, on the vertical axis of the beam and connect them either by straight line or by curves. So let's do this now. So this is the beam here. We had point A here. This is point A. There was a concentrated force, and then point B, and then here this is point C, and then point D. Those are the key points. Okay. Now I'm going to start drawing the bending moment diagram. Just plot the moment at the key points. How much is the moment at point A? 0. So here, I'm just going to plot 0. Point B, how much is the moment at point B? We calculated point B, the moment at point B. How much was that? Negative 120. So I'm just going to plot at point B, negative 120. So I'm just going to go down here. This is 120 kilonewtons meter. It's negative. Okay? And then at point C, how much was the moment at point C? Positive 120. So I'm just going to plot positive 120 kilonewtons meter here. And then point D, how much was the moment at point D? 0. So I'm just going to plot 0 here. So those are the 4 key points. Those are the value of the moment at the 4 key points. I just have to connect them. Okay? Each 2 consecutive points, I just have to connect them, either by straight line or a curve. So from point A to point B, should I use a curve or straight line? From point A, to answer this question, from point A to point B, are there loads between point A and B? Yes, there is a uniform load from point A to point B. Then it's a parabola. If there is no forces between point A and B, then it's a straight line. Okay? That's straightforward. Okay? So there is a parabola here. Okay? So how much is the height of this parabola? How to draw this parabola? To draw this parabola, you're going to connect the 2 points by a dotted line, and then from the middle of that line, you're going to draw a height here that is equal to W L squared divided by 8 of that uniform load. W, the intensity of the load, was 20 kilonewtons per meter times the length from A to B, which is 6 meters squared divided by 8. Okay? So that's 90 kilonewton meters. So that's the height here. So you get this 3rd point, and then you draw your parabola to pass by the 3 points. Okay? From point B to point C, there is a uniform load. So there is